By convention, if the result of a measurement is reported without its uncertainty explicitly stated, then the uncertainty is said to be to the nearest 1/2 of the smallest division of measure. If we have something reported as 5 centimeters, then we are going to assume that the smallest division of measure is in the ones place. So we are assuming that this was made with a device whose divisions are spaced at 1 centimeter marks apart. The smallest division of measure being in the ones place says the difference between two of our marks is 1 centimeter. If we're measuring something using this measuring device, it's okay to round to the nearest half of the smallest division of measure if we could clearly and reliably do so. So for the length of this piece of string I just drew above the ruler, we could estimate that piece of string to have a length of 2.0 centimeters plus or minus 0.5 centimeters. Here I'm estimating to the nearest half of a centimeter. And for me, it looks like it's closer to 2 centimeters in length than it is to 2.5 centimeters in length. So we could follow the rules of significant figures. The rules of significant figures says if we could reliably measure to the nearest half of the smallest division of measure, and in this case, that smallest division of measure is the 1 centimeter, because that's the difference between two of our ticks on our ruler, we could then report the result of this measurement as a single number, 2 centimeters. 2 centimeters, again, if we look at this 2 centimeters is in the ones place. That's the smallest digit, the most precise digit. It's the only digit. That's to the ones place. Since it's to the ones place, our uncertainty can be given to plus or minus 1/2 of that 1 centimeter, which is plus or minus 0.5 centimeters. If we had a value that was, let's say, 5 centimeters, that 5 centimeters is equivalent to 5.0 centimeters plus or minus 0.5 centimeters. If we had a value that was 32.3 seconds, that is equivalent to 32.30 seconds plus or minus 0.05 seconds. Why that is our most precise decimal place there is to the 10th place. So that is to the 10th place. That means our uncertainty can be written as plus or minus 1/2 of a 10th of a second, which is plus or minus 0.05 seconds. Significant figures is a shorthand way of expressing a number whose uncertainty is given to be 1/2 of the smallest division of measure. So again, for another example, if we had something with a mass of 2.3 kilograms, our most precise digit is our smallest division of measure is going to be considered to be in the 10th place. And actually, let's change this example a little bit, since we already did something to the 10th place. Let's say we did something to the 1000th place. The thousandths place is 0.001. So that means our uncertainty is going to be equal to plus or minus 1/2 of a thousandths. This means our uncertainty for this value is plus or minus 0.0005 seconds, and we could report our value to the nearest 0.0005 seconds. So that's equivalent to 2.3150 seconds plus or minus 0.0005 seconds. Notice the decimal place of the uncertainty matches the decimal place of our best answer, our best estimate. And this is equivalent to simply writing 2.315 seconds. So if we could reliably report our uncertainty to the nearest half of that smallest division of measure, then it's more compact to write our numbers like this because the uncertainty is assumed to be in that last decimal place. So the number of decimal places indicates the precision in which the data is known. So for this number, 2.315 seconds, since it goes out to the thousandths place, we have a certain amount of precision there versus a number that was only going to the hundredths place. We have less precision in that number. So the number of decimal places really tells us how precise we're doing our measurements. The number of significant figures in a problem is limited only by the measured value of the problem. Or the measured value. The number of significant figures is limited only by the measured values in a problem. So if we're using problems that have a mix of 2 and 3 and maybe 4 significant figures, then our final answer is going to be limited based off of those numbers, because those numbers have and communicate the amount of certainty we have in those values. Exact numbers, integers, and defined numbers have an infinite number of significant digits. For example, I could have a black jelly bean, I could have a red jelly bean, I could have a green jelly bean, I could have a blue jelly bean. I have exactly 4 jelly beans. There is no uncertainty in that. I am absolutely confident with 100% assurance that I have 4 jelly beans. So this counting is an exact number. It is exactly 4, which is an integer. So we could consider this number 4 to have an infinite number of significant digits. There is no uncertainty in this value. Any digit that is not 0 is significant. So digits that are not 0 are numbers between, let's say, 0 and 10. So the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Obviously, the number 10 is not 0. However, one of the digits in 10 is 0. So we'll have to figure out how to handle that 0. Significant figures rely on our ability to determine the number of significant digits, because in order to use this convention of plus or minus 1/2 the smallest division of measure, we need to be able to count the number of significant digits. So basically, the digits that are significant always are any non-zero digit, and our non-zero digits range from 1 to 9. Which means 0, here let me write significant, which means 0 is, well, for now, I'm not going to say it's insignificant, because whether 0 is significant or not depends on a few things. So the only thing we could say right now with certainty is that non-zero digits are considered significant. So for example, the number 549 has 3 significant digits, 5, 4, and 9. The number 1.892 has 4 significant digits, because 1, 8, 9, and 2 are not 0. The number 4023, well, we don't know yet. We know it has at least 3 significant digits. It may have 4 significant digits. We're going to know for sure soon. But right now, with the rules that we have, we know that non-zero numbers are significant. So we know this has at least 3 significant digits. Same thing with the number 420. The number 420 has at least 2 significant digits. The reason why I say at least is we don't know how to handle that 0 yet, but we do know 4 and 2 are significant. Zeros between non-zero digits are significant. Okay, let's revisit the previous slide. This number 4023. Notice where the 0 is. The 0 is between non-zero digits. So anytime a 0 appears between non-zero digits, you count it as being significant. So this number does have 4 significant digits. If we had the number 1.017, that 0 appears between a 1 on the left and a 1 on the right, both of which are not 0. So we could say this number has 4 significant digits as well. Zeros to the left of the first non-zero digit are insignificant. Well, let's take the number 0.01 meters. So both of these zeros are before the first non-zero digit. So both of those zeros are considered to be insignificant, which means that this number has only one significant digit. Let's look at the number 0.000034 meters. All of these zeros are to the left of the first non-zero digit, so all of those zeros would be considered insignificant, which means that this number has just two significant digits. For numbers with decimal points, zeros to the right of a non-zero digit are significant. Let's take the number 2.00 seconds. This decimal point even though we have zeros in this number, because they are to the right of the number 2 and we have a decimal point, these would be considered to be significant. Because numbers with decimal points, zeros to the right of a non-zero digit, are significant. So that means this number has 3 significant digits. If we take the number 0.050 seconds, well, these numbers to the left of the first non-zero digit are considered insignificant. But this number to the right, this 0 to the right of 5, is considered significant. So this number has 2 significant digits. Here's where the rule becomes ambiguous. What if we don't have a number with a decimal point? Let's say we have the number 400 centimeters. Are those zeros significant or not? Well, for numbers without decimal points, trailing zeros may or may not be significant, depending on the convention used. Now, a textbook in one class might have one set of conventions for how to handle zeros, while textbooks in another class might follow a different set of conventions. So it's important to know the convention that's being used, because how we report our answer is going to be based on that convention. The convention that we're going to use is that trailing zeros for numbers without decimal points are insignificant. So for this number 400, no decimal point is explicitly listed in this number. We have one non-zero digit, so the 4 is significant. These zeros trail behind the 4. These zeros will be considered insignificant. And so this number has only one significant digit. Now, if we explicitly wrote a decimal point, let's say 400 with that decimal point, this number is going to be considered to have 3 significant digits. Because zeros between a non-zero digit and the decimal point are considered significant. For the number 410 centimeters, this number is going to be considered to have 2 significant digits because no decimal point is explicitly listed. But 410 decimal point is going to be considered to have 3 significant digits, because we have a 0 between a non-zero and a decimal point. Now, the one reason why you can maybe see why we're going to treat those trailing zeros as being insignificant by looking at our convention in reporting a measured value. Remember, in reporting a measured value, we report our best estimate of that value plus or minus the uncertainty in the estimate of that value. And remember, for numbers that don't have the uncertainty explicitly stated, we are going to take the uncertainty to be plus or minus 1/2 the smallest division of measure. For the number 400, it is assumed that the division of measure is in the hundreds place. So this is plus or minus 1/2 of 100 centimeters, which is plus or minus 50 centimeters. So in reporting this value x, we are really reporting that we believe that that value is somewhere between 350 centimeters and 450 centimeters. Looking at this on, let's say, a ruler, this will be our 400 centimeter mark. This will be our centimeter ruler. This will be 450 centimeters, and this will be 350 centimeters. Okay, I need to extend this to the left so it can actually represent what I want it to represent. So this is obviously not to scale. Our uncertainty means that our true value is somewhere in that range. We don't know if this measurement, if the true value is 351 centimeters, or 412 centimeters, or 399 centimeters. So those different values all are within our uncertainty. So to report to the nearest ones place or even the nearest tens place would be inaccurate because we are uncertain in those decimal places. We don't know if it's 422 centimeters. We don't know if it's 376 centimeters. All we know is it's somewhere between 350 centimeters and 450 centimeters. So to report that, or because that is our limitation, this is why we are going to consider these zeros to be insignificant. Now that we know how to treat zeros, let's work on adding and subtracting numbers that have significant figures in them. Let's start off with two numbers. Let's start off with the number, let's see, the number 5 centimeters. And we will say we have the number 7.1 centimeters. I'll call the first number our first length measurement, and I'll call the second number our second length measurement. Now, using the rule of uncertainty in significant figures, we know that 5 centimeters is equivalent to 5.0 centimeters plus or minus 0.5 centimeters. And we know that 7.1 centimeters is equivalent to 7.10 centimeters plus or minus 0.05 centimeters. If we were to add these two numbers, the 7.1 centimeter and the 5 centimeter, we would end up getting the value of 12.1 centimeters without rounding. However, to report our answer as 12.1 centimeters is incorrect. It's misleading. It's communicating to someone else that we know the result to the nearest tenth of a centimeter. And that's not true, because one of our values, we can know it no better than to the nearest half of a centimeter. And so if we're reporting our result to the nearest tenth of a centimeter, we are miscommunicating. We are being misleading. Let me show you why that is so. Let's draw a measuring device. Let's say this measuring device is just indicating the uncertainty in our measurements. We will set the 0 to be right in the middle. This will measure in centimeters. The left edge will correspond to minus 0.5 centimeters, and the right edge will correspond to plus 0.5 centimeters. The uncertainty in our first measurement is plus or minus 0.5 centimeters. So when we report our first measurement to be 5 centimeters, that means our true value is somewhere between 4.5 centimeters and 5.5 centimeters. We don't know if it's 4.7 centimeters or 5.3 centimeters. We just know it's somewhere in that range, and we have no idea about the tenths place really. Well, let's look at our second uncertainty on this same measuring device. So I'm going to add some tick marks. And our second uncertainty is to the nearest half of a tenth of a centimeter. What that looks like on this scale is our uncertainty for that second measurement is somewhere in that range, to the minus 0.05 to the plus 0.05. Notice the difference between those two uncertainties. Even though we know that the second length measurement is 7.1 centimeters to the nearest tenth of a centimeter, our second value, or really our first value, the 5 centimeters, has such a large uncertainty. We can't round our answer to the nearest tenth of a centimeter. We have to round our answer to only the ones place, because that's the digit that we are certain to. We're certain to the ones place. We can't say our answer is 12.1 centimeters because the uncertainty in the 5 centimeters is so great. So when adding and subtracting numbers with uncertainty, look at the decimal places. Go ahead and add your two numbers together and don't round yet. Only round when you're deciding on how to express your final answer. And how we're going to do this, what helps me visually is to kind of do a vertical line that splits my unknown decimal place and my reported decimal place. So this right here, we don't know what that value is for the number 5. So what I'm going to do is draw this vertical line, and I'm going to keep things on the left, and I'm going to discard things on the right. So we would report this value as 12 centimeters. Let's do another example. Let's say we had something that was 32.875 seconds. And let's say we had something that was 110 seconds. Let's add these two numbers together. So in adding these two numbers together, we would get 142.875 seconds. However, for this number, since we have, for the number 110, since the 0 is insignificant, because the number 110 does not have a decimal point indicated, and that 0 is to the right of a non-zero digit, we know that 0 is insignificant. So when I report the final result based off of this addition, since that 0 is insignificant, I am going to discard anything to the right of the line. And what I mean by discard, I'm going to round to that. So maybe I should have said round up here instead of discard. Because it's not that we're totally throwing it away. We're just going to round such that we have a number on the right, and we're not going to have any numbers or zeros on the left, depending. So in this example, our result would be 140 seconds, because we are rounding to the nearest tens place, because that's where the uncertainty is in our second number. When two numbers are multiplied or divided, the number of significant digits in the result is the same as the least number of significant digits in the numbers that are multiplied or divided. So let's take the number 21 times 3. 21 has two significant digits, so we'll say it has two significant figures. The number 3 has one significant digit, so one significant figure. Let's multiply these numbers together, so when we multiply them together, the result is 63. But because one of the numbers has one significant figure, we're going to need to round our answer to one significant figure. So even though the result of our calculation is 63, there is uncertainty in the number 3 that we used in our calculation. And that uncertainty is so large, we're going to need to round our number to one significant figure. So in this case, we would round to 60. If we had 3.2 times 2.87, and we will say this is in meters, and if we are multiplying those two numbers together, okay, let's go ahead and do that. 3.2 and 2.87. 3.2 times 2.87. We get 9.184. So 9.184 meters. It would be misleading for us to report our final answer to that number of decimal places, even though that's what my calculator showed. Because the top number has only 2 significant digits. The bottom number has 3 significant digits. Because when two numbers are multiplied or divided, the number of significant digits in the result is the same as the least number of significant digits in the numbers that are being multiplied or divided. Since the least number is 2 significant digits, we will express our final answer having 2 significant digits.